All right. Good afternoon. Sorry for the late start. I'm juggling the aftermath of back-to-back midterms and online life. So, happy Friday. Yes, I am muted. Thank you. Appreciate that. All right, so welcome to CSE215. Hope everyone's doing well. Sorry for the late start. Dealing with post-midterm exam issues and such. So anyway, hopefully everybody can hear me now. So a few things up front. First of all, I posted a video on the regular YouTube channel that goes through doing an RSA calculation by hand. And it's not something you need to watch, but if you're curious, we went through the theory of RSA and some of the math that shows how decryption works and so on. We went through that on Wednesday. If you want to see it applied to an actual case, I took, a two-letter message and came up with an encryption key and then calculated the decryption key, encrypted the message into ciphertext, and then used the decryption key to decrypt it back into plain text. And that's about a 30-some minute video. It's not time I wanted to spend in class, but I wanted to go through it anyway. And all the calculations are done by hand using a pocket calculator. So it's perhaps a good example of not only RSA, but modular exponentiation, using Euclid's algorithm to find greatest common divisor and to find our decryption key. And then some tricks for using a calculator to do modular calculations on potentially large numbers. So that's posted on the regular channel. If you're interested, go ahead and have a watch. All right, let's see. So we had a question about quantifiers. And in particular, trying to relate quantifiers to kind of real-world situations. Let's see. Without actually doing the grandmother question, let me see if we can think of a similar, or maybe I can find a similar question in the book. So let's try question 9, which I did not assign. Use quantifiers to state that the sum of any two rational numbers is rational. So the sum of any two rational numbers is rational. So what is this saying if we think of it in terms of for all or there exists? Any two rational numbers added together gives us a rational number. So one way we could do this would be just to say, for all x comma y contained in the set of rationals, x plus y is also contained in the set of rationals. If we wanted to state this in a more complex term, for all x comma y contained in the set of rationals, there exist m comma n contained in the set of integers such that x plus y equals m divided by n. So there's a nested quantifier approach. Okay, because how do I say that every mom has a grandmother? Yeah, you're allowed to use multiple variables. You can create new variables and use those. And in fact, we often do, just like we're doing here. Does that help? Don't ever stress about discrete structures. It's too fun of a subject to stress over. But yeah, cool. Okay, good, awesome. Thank you for the good suggestions in chat. All right, any other questions? All right. Well, let's move on to our next topic. So so everything we've done up to this point is fair game for the midterm. Okay. The homework I give out on Monday will be related to more of the number theory stuff. Unfortunately, that won't get graded and handed back to you until after the midterm. But the questions you see on Monday's homework are possibly representative of questions you'll see on the midterm. So I say this every week, but it's even more critical next week. You're going to have to work on the homework questions early in the week so that you can ask questions about them, because you're potentially responsible for knowing how to do those questions on the midterm. What we're starting today, which is mathematical induction, will not be on the midterm. All right, so beginning with today's topic, this is stuff that will be for the final exam, but not the midterm. But everything up through before today's class, all the number theory stuff, GCDs, Euclid's algorithm, Fermat's little theorem, all of that, fair game for the midterm. All right, so new topic. So this will be something we'll talk about for a while, mathematical induction. Let's see, question, can you post homework today so we can get started this weekend and ask questions on Monday? I can't post it today, but I will post it tomorrow. How about that? And then you'll have a chance to work on it over the weekend, Saturday. Good suggestion. All right, mathematical induction. This is, in some ways, at least one of the three most important things in this course, if not the most important. The main things that I want people to come away from this course understanding are logical reasoning, right? Logical arguments, i.e. proofs, and mathematical induction, right? Which is really just another aspect of logic, but it's a particular area. Induction is a really powerful tool. It's a tool that we already, to some degree, understand and use intuitively. Okay, but we're going to make it fairly formal and rigorous and see exactly what this is all about. And this is something that feeds into computer science and programming. When you write an algorithm that you believe is going to work in a number of cases, a lot of times you're using an inductive proof in your head to convince yourself that this code is correct. So we want to make that a little more formal. When we start dealing with recursion, which will be, you know, everything we do in data structures in winter, CSE215, recursion is really just the computer science analog of mathematical induction. And so the more you understand this, the more successful you're going to be in these other areas. And as you study recursion, you'll look back on this and mathematical induction will start to make more sense. And it's not a binary thing. It's not like I get it or I don't get it. It's one of these things, at least in my experience and from what I've seen, it's one of these things that builds over time. Your understanding of it becomes better and it evolves, and you can be more successful in using this. So that's kind of the general roadmap for at least the next few classes. But we'll come back and use mathematical induction pretty much the rest of this course. All right, let me start off with an example, and then I'll give you a kind of formal definition of induction, and then we'll start working through some specific examples. But let's start with a kind of a thought exercise. So imagine an infinite ladder. Infinite number of rungs on this ladder. Okay. So what does that mean? It means that if you look at the nth rung, there's always rungs above that as well, whatever n you pick. If you climb up to the billionth rung of this ladder, there's still going to be more rungs above you. Okay, that's what infinite means. All right. So you have an infinite ladder, and you want to know if you can get to the 10th rung of this ladder. Well, so we're going to be given the following proposition. If you are on rung n, and does everybody know what I mean by rung? It's just one of these steps that you step on. So each of those is a rung. So if you're on rung n, you can reach rung or step n plus 1. So that's a proposition that I'm giving you as true. Basically says you can always climb one step up. If you're here, you can get there. If you're here, you can get there. And we can believe that's true, right? Most of us have climbed ladders, and if we haven't, we can figure it out pretty quickly. And you know, pretty much no matter how tired you are, no matter how far off the ground you are, if you're on this step, you can get one step higher, right? You just lift a leg, put it on there, push yourself up, move your hands. All right? So this is a given proposition. I'm stating that this is true. If you're on rung n, you can get to rung n plus 1. Okay, so here's a question. Can you reach the 10th rung? So what do you think? Give me some dialogue in chat. All right, so some really good answers here. And all of these answers are good, and all of them are topical to the kind of details we're going to talk about. So the first answer was, of course. And yeah, I mean, how hard is it to get to the 10th rung? You get to the first, the second, the third. You do that 9 times, and you're on the 10th. Somebody else said, if we can prove that we can get to the first. Okay, and this is a good part. If this ladder is on the roof of a very tall building, and we don't have any way to get to the roof, we cannot get to the 10th rung. So even though it seems really clear from this that we can get to rung 10, it doesn't really mean anything unless we know we can get to the first rung, or maybe the second rung, or the 9th rung, but some rung below 10. Okay, which was another comment. You have to start below rung 10. So we need another proposition. You can reach rung 1. All right. If we're given this proposition along with that, then absolutely we can reach rung 10. Right? How would we prove that? Well, we know we can reach rung 1 because we've been given that. And we know if we can reach rung 1, we can reach rung 2. Therefore, we can reach the second rung. And we know if we can reach rung 2, we can reach rung 3 because of this proposition. So we can reach rung 3. And we take 10 lines of proof, and the last proposition will be we can reach rung 10. And that'll be our proof. All right, everybody comfortable with that so far? Now suppose I had asked, can you reach rung 100? Could you prove that? An absolutely airtight proof given this and that? Sure. But your proof would be 100 lines long. But I don't think any of us doubt that we could do that. Even though we've never written a proof for that probably in our lives. I've never written a proof for that. I don't know if anybody's ever written a proof for that. But we can kind of see that if we had a big enough sheet of paper and enough time, we could start with, you can reach rung 1, and then we could say, by this proposition, you can reach rung 2. And after writing out 100 statements, we would have proven the proposition, you can reach rung 100. So using these two propositions, we can absolutely prove that you could reach rung 100. All right, what if I wanted to reach rung 1 billion? Could we write a billion-line proof to conclusively prove that this is reachable? Absolutely. I'm not going to do it, but we could do it. And I think we can clearly see in our heads that there's no reason we can't do what we did for 10 or 100 and just extend it to 1 billion. And so we might write the first few lines of this and then say, dot, 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 repeat this, 997,999,997 times. But how do we make an airtight proof out of this without saying dot, dot, dot? Because when we say dot, 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 almost always what we mean is, I've got something in my head, you know what it is, I'm not going to write it out. Well, that's not valid in a proof. That's the whole reason that proofs fall apart. You know what I mean, it's obviously true, right? As soon as someone says that, instead of spelling it out formally, there's a good chance that what they're trying to prove can't actually be proven. All right, so how do we know we can reach the billionth rung? Let me give you a different example. If you grab a pocket calculator and you say 1 plus 1, you end up with 2. And we've done this, right? As long as it's not equal to 5. 1 plus 1 equals 2. And if I grab a pocket calculator and I say 1 plus 1 plus 1, my display is going to show 3. And if I do 1 plus 1 plus 1 plus 1, my display is going to show 4. Okay, if I did this a total of 10 times, everybody agree my display would show 10? And I think probably when my family got their first pocket calculator, which was, in the early 70s, I probably added 1 to itself 10 times. I think I discovered the constant function. And you just keep hitting plus and it would keep adding so it would count. So, at least once in my life I've actually done this. And other people probably have too. All right. Suppose you were to press the 1 plus 1 1,000 times. How do you know you would end up with 1,000? Unless you've actually done this, how do we know that's what's going to happen? Time to do it. No, don't do it in class. You'll miss all the other good stuff. You could make a Lego machine that keeps hitting the plus button and does that 1,000 times. Yeah, so certainly this is going to tie into mathematical induction. But why do you believe that adding 1 to itself 1,000 times will give you 1,000? I mean, I assume people believe that. I believe it. I have my own reasons for believing it. But why do we think that's true? That's a good answer. It's how you were raised. What's the underlying mathematical or arithmetic fact that makes this equal to 1,000? Or that would make this equal to 2,000. Yeah, multiplication, right? So when we add something 1,000 times, we're multiplying that something by 1,000. If we add 2 together 1,000 times, we're multiplying 2 by 1,000. And as long as we believe that 1,000 times 1 is 1,000, this is airtight. So we could generalize this, and we could say if we take 1 n times, that's equal to n times 1, which is n. But this is something we've never proven. And we're kind of getting down to like fundamentals of arithmetic and how do we know things that we know are true. How do we know that adding this n times will be the same as n? Well, it turns out we can prove this. The same way we can prove that we can reach the nth rung of a ladder. So we're going to prove this using 2 statements. So I'm going to give you 2 propositions. Proposition 1. Proposition 1 says if the sum of n ones is equal to n, then the sum of n plus 1 n's is equal to n plus 1. In other words, if this funny property of adding 1 n times gives us n, if that works for some number n, it's also going to work for n plus 1. And intuitively, that's pretty easy to see because n plus 1 ones would just be this plus 1 more 1, which would be n plus 1 more 1, which is this. So this is pretty easy to understand and accept. If we add n ones to get n, if that's guaranteed to be true, then if we do n plus 1 ones, we'll get n plus 1. Okay, so if we believe this proposition, and we also know that 1 plus 1 is equal to 2, then without using a pocket calculator, we can do the same thing we did with the ladder. We can start off by saying, so let me call this P1 and P2, and let's prove the sum of 5 ones is 5. Okay, so 1 plus 1 equals 2, that's proposition 2. 1 plus 1 plus 1 equals 2 plus 1, that's proposition 1. And I'll just restate that as 1 plus 1 plus 1 equals 3. And then I'll use proposition 1 again and say 1 plus 1 plus 1 plus 1 equals 3 plus 1. And then I'll use proposition 1 one more time. And we're done. So for any given n, if you want to show that the sum of 1,000 ones is equal to 1,000, I can do that by just using these two propositions and doing about 1,000 lines worth of work. Maybe 2,000 if I take 2 lines for each step. Alright, so I can prove sum of 1,000 ones is 1. How do I prove the sum of 10,000 ones is 10,000? Well, I could do a longer proof. How do I prove the sum of 1,000,000 ones is 1,000,000? I could do a 1,000,000 line proof. Alright, so for a particular rung, I can prove that you can climb there. For a particular n, I can prove that this sum is equal to n. But we don't have a way to generalize it yet. Okay, the way we generalize it is a theorem called mathematical induction. So mathematical induction is a really powerful theorem, and let's state it formally. So what does this say? Given that some proposition P of n implies P of n plus 1, and given that P of 1 is true, then P of n is true for all n bigger than or equal to 1. Alright, so let's break this down. First of all, what is P of n? P of n is one of these families of propositions like we talked about with quantifiers. So P of n is a family of propositions. For example, let P of n be the proposition 1 plus 1 plus 1 n times equals n. And these dot dot dots are sloppy, so if I wanted to write this formally, I would write this as sum from I equals 1 to n of I is equal to n. But I'm using dots because I want to stay kind of, I don't want to get bogged down in math and in the examples here. Alright. So P of n is a family of propositions. P of n could be the proposition that you can reach the nth rung of a ladder. So P of n is the proposition you can climb to rung n on a ladder. What mathematical induction tells us is that if we know that P of n implies P of n plus 1, in other words, if knowing that you can get to rung n means you can get to rung n plus 1, and also we know that P of 1 is true in this case, and you can get to the first rung, then we can absolutely conclude P of n is true for all n bigger than or equal to 1. In other words, you can reach the nth rung of the ladder for any positive integer n. That's mathematical induction. So we're going to start with a family of propositions, and we're trying to show that this family of propositions is always true, that every proposition in that family is true, for example, for all n bigger than or equal to 1. And that's a hard thing to do. To prove each of those propositions takes an infinite amount of work because there's an infinite number of those. So proving them one by one is not feasible. But we only have to prove two things. We have to prove that P of 1 is true, or P of some particular number is true, and then we have to prove this slightly weaker statement. This statement here does not say P of n is true for all n. It says that if P of n is true for some n, then it's true for n plus 1 also. And that's an easier thing to prove, right? That's the difference between showing you can climb any ladder no matter how tall it is versus showing if you're here, you can get there. Well, that's an easy thing to prove in comparison. You just have to show that you can lift your leg and pull yourself up one rung. Whereas proving P of n for all n says for any ladder you can imagine, you can climb, you know, up to the top of it. Or you can climb to any rung on an infinite ladder. All right, so this is the formal statement of mathematical induction. Okay, given a family of propositions, and given that P of n implies P of n plus 1, and P of 1 is true, then P of n is true for all n bigger than or equal to 1. And we can actually restrict this to all n bigger than or equal to 1. All right, so this is called the inductive step. P of 1 is called a base case. And you got to have both of those. Certainly if you don't have the inductive step, all you've got is you can get to, you know, the first rung on the ladder, or P of 1 is true. But the inductive step alone is not enough. You've also got to have a base case. So in the case of a ladder, right, being able to climb from rung n to n plus 1 doesn't get you to any rung you want unless you can also get on the ladder to begin with. So if it's on the top of a building and you can't reach it, P of 1 is not true, and you can't prove that you can get to the 10th rung or the 100th rung or the 1000th rung because you can't even get to the first rung. In the case of adding up ones, let's look at this. I claim that 1 plus 1 plus 1 n times equals n plus 17. Is there a proof for this? Let P of n be the proposition 1 plus 1 n times equals n plus 17. Well, if P of n is true, then this is also true. Right? If I add up n ones and I add one more 1, which is n plus 1 ones, that's equal to n plus 1 plus 17. That's what P of n plus 1 says. So we can prove that if P of n is true, P of n plus 1 is also true. But that does not prove this claim. If it did, we'd have a problem, because 1 would equal 18. Right? We can prove this, we can prove the inductive step, but unless we can also prove a base case, we can't claim P of n is true for anything. And there is no base case for here. P of 1, or P of 2 says 1 plus 1 equals 19, and that's not true. Right? So there's no base case, so we can't argue mathematical induction. All right, so you got to have both the inductive step and the base case. We'll come back to that in another lecture. All right, questions about that? That's the basic setup. That's what we're going to do for about a week now, is look at mathematical induction, look at some of the things we can prove with it, look at some of the pitfalls around it, and so on. So we're just getting started on this, but questions up to here. All right. So before we jump into using this and exploring it, let's talk a little bit about why it works. And this is not super critical. We can take it on faith. But let's look a little bit at why it works. And this gets into some pretty edgy mathematics / philosophy, but we'll keep it kind of light for a Friday. Why does it work? So suppose P of 1 is true, and in this course or any logic course, right, if I say suppose Q, where Q is a proposition, that really means suppose Q is true, okay? This is like in programming, if we have Boolean variables, if we say if X, we really mean if X is true, right? So suppose P of 1 is true, and suppose P of n implies P of n plus 1 for all n bigger than or equal to 1. So suppose we have a base case and we have an inductive step. Okay. But suppose also P of m is not true for some m bigger than 1. So suppose mathematical induction has failed us. This is a proof by counterexample. Okay, we want to prove that mathematical induction works. Well, mathematical induction says given P of n implies P of n plus 1, and given P of 1, then P of n should be true for all n bigger than or equal to 1. Let's negate the conclusion. Okay, so suppose there's some integer m bigger than 1 for which P of m is not true. Okay, so that's negating the conclusion, and we're going to find a contradiction, after which we'll have to conclude P of m is true for all m bigger than or equal to 1. And this is pretty straightforward to do. So let B equal the set of all integers b, little b, such that P of b is false. All right, so we're supposing, you know, we've got a base case, we've got an inductive step, but there's at least one integer for which P fails to be true. Okay, I'm saying let's take all the integers for which it fails and throw it into a set called B for bad. So this is a set of all the values of B, all the integers where the proposition fails to be true. Okay, well, B is not the empty set. Why? Because we know there's at least one element m in it. All right. Well, since B contains only positive integers, and it contains at least one element, we have the following fact, but I'll put fact in quotation marks. There exists a smallest element, S, in B. So just think about it intuitively. Suppose you take any set of positive integers, and it can have an infinite number of elements, but every element in that set is a positive integer. Can you always find the smallest element in that set? Absolutely. Now, if we allowed negative integers, no. I mean, numbers could keep getting smaller and smaller, and you'd still find smaller ones. But if every integer in that set is bigger than 0, there is a smallest element. All right. So we're going to work with this fact for a moment. There exists a smallest element in the set. I'm going to call that S for smallest. All right. Well, there's two possibilities. Possibility 1. S is equal to 1. Well, that's not a possibility because we know that the proposition is true for 1. So 1 cannot be an element of the set of bad elements. So let's call that possibility 0, and let's say no, that's not a possibility. So possibility 1, S could be equal to 2. Well, that's actually not possible either, because since we know 1 is a value for which P is true, and we know that Pn gives you Pn plus 1, since P1 is true, we know P2 is also true. So S cannot be equal to 2. Alright, so our only other possibility is that S is an integer bigger than 2. Well, if S is the smallest number for which the proposition fails to be true, that means P of S minus 1 must be true, because S minus 1 is smaller than S, right? And it's a positive integer, so P of S minus 1 is true. But now we know from this statement that if P of S minus 1 is true, then we know P of S minus 1 plus 1 is also true, which means P of S is true, which means S is not in the bad set. And that's a contradiction, because S was in the bad set. In particular, it was the smallest element. So intuitively, all that this is saying is, given P of 1 and given Pn implies Pn plus 1, if there's some point, some place on the ladder that you can't reach, some n for which the proposition fails, just keep backing up until you get to the smallest, the first case where it fails. And since the previous case is true, this proposition implies that that next case must be true also. So it can't have failed. So that's the argument for why induction works. But let me just take one moment and take a look at this. So I call this a fact, but I put it in quotation marks. It's not actually a fact in the guaranteed to be true kind of way that we like to use the word fact. What this is really is an axiom. And it's called the axiom of well-ordering, or the well-ordering axiom. And the well-ordering axiom says if you have a set of positive integers, there's always a smallest element. It turns out we can't prove that. If you had mathematical induction, you could prove it, but you don't know that mathematical induction is true unless you have this axiom of well-ordering. So this is something we cannot prove. This is something we simply accept. And the foundation of all mathematics comes down to axioms, things that we accept. And if we choose not to accept them, or to accept something contradictory to that, we come up with a different version of mathematics. And this is how mathematics is. So we don't know that there's always a smallest element in any set of positive integers, but we simply choose to believe that there is, and we develop mathematics from there. And one of the things we get from there is mathematical induction. I'll mention one other axiom here just to make Friday more interesting. This is called the Axiom of Choice. And let me give you a kind of common spoken description of the Axiom of Choice. Suppose you have a set of anything that's considered a valid set. Could be integers, could be colors, could be colleges, but it's a set, right? Is it possible to pick an element out of any set? Given any set, can you pick an element out of it? What do you think? Doesn't matter which element, just any element. Is that possible? Yeah, any one element. Doesn't matter which one. Sure, I mean, you know, put down a bunch of pennies that are different from each other and ask someone to pick a penny, they can pick a penny, right? And if we have particular sets, like if we have a set of positive integers, we could pick the smallest element. If we have a set of words, we could pick the first word that occurs alphabetically, or the first word alphabetically that begins with the letter Q, right? So long as it has at least one element, it's got to be a non-empty set. So S is a set, and it's not equal to the empty set. Can you pick an element? And for particular sets, we can sometimes find algorithms for doing that. But in general, for any set, we don't know that you can always pick an element. And there's no way to prove that you can always do that. It's something that you either assume or you don't assume. And so if you assume that you can always pick an element from a set, that's called the axiom of choice. And you can do an entire development of set theory assuming that axiom of choice, or AOC, is true. You can do a parallel development of set theory where you don't assume axiom of choice. And you sometimes get to slightly different places. And there's a whole bunch of things. There's something called Zorn's lemma that can be shown to be equivalent to the axiom of choice. There's all these low-level fundamental things that we take to be facts, but that in fact are matters of faith. And the well-ordering principle is one of those, and the axiom of choice is another. And this intrigued me when I first encountered it, because to me it somehow smacks as some kind of relationship to free will, right? Can you actually just pick an element without following some prescribed program that tells you what element to pick? Well, if you can do that, then you should be able to pick any element from a set. But apparently we can't prove that using rigorous logic. All right, that's a bit of a sidebar, but that's something to think about during your weekend if you like. Let's go back to mathematical induction. So let's start looking at some examples of what we can do using mathematical induction. So let's look at some sample proofs. And we're going to alternate here between some very mathematical looking questions, and some very non-mathematical looking questions. I'm going to start with a mathematical example because those are a little easier to make rigorous. And then we'll go on to some ones that are don't feel like mathematics at all, perhaps. Okay, so here's a family of propositions, and we're gonna really need to focus on sticking to what a proposition here. A proposition has to be a declarative statement. So if I say, you know, n plus 1 squared equals n squared plus 2n plus 1, that's a proposition. If I write n plus 1 squared minus 1, that's not a proposition. Okay, this is a declaration because I'm saying that these are equal to each other. This is just an arithmetic expression. All right, so example application, sum of integers. So let P of n be the proposition. The sum from I equals 1 to n of I is equal to n times, and I always have to think whether it's plus or minus, so 1, 2, 3, n times n minus 1 divided by 2. I feel like that should be a plus. 1 plus 2 plus 3 is 6. That's 3 times, yeah, that's a plus. All right, so our proposition P of n is that the sum of the integers from 1 to n is equal to n times n plus 1 over 2. And we can sanity check that, right? We can say example. P of 4 says 1 plus 2 plus 3 plus 4 is equal to 4 times 5 divided by 2. Well, 1 plus 2 is 3, 3 is 6, 4 is 10, 4 times 5 over 2, 20 over 2 is 10. So, you know, P of 4 seems to be true. P of 3 seems to be true. It says 1 plus 2 plus 3 is 3 times 4 over 2. That's 6 on both sides. But we want to prove this. Okay, so prove P of n for all n bigger than or equal to 1. And I'm restricting myself to integers. I'm not going to keep writing n contained in z. Okay, until further notice, we're just going to deal with integers. All right, so if we want to prove this using mathematical induction, we only have to prove two things. All right, we have to prove a base case, P of 1 in this case, and we have to prove Pn implies Pn plus 1. All right, let's start with the base case. So step 1 will be the base case. So let's prove P of 1. Well, we're only trying to prove this proposition for one given value of n, so we can just plug in n equals 1 and see if the proposition is true. But we're going to do this very carefully, right? I'm going to say P of 1 says the following. It says the sum from I equals 1 to 1 of I is equal to 1 times 1 plus 1 over 2. Okay, all I've done is plug a 1 in for n in the definition of P of n. Sum from I equals 1 to 1 of I is equal to 1 times 1 plus 1 over 2. Okay, now I'm just dealing with plain numbers here. Okay, so I'm going to show that this side, I'm not going to transform these, I'm just going to show what they're equivalent to. Sum from I equals 1 to 1 of I is just 1. And 1 times 1 plus 1 over 2 is 1 times 2 over 2. That's equal to 1. So this expression is exactly equal to 1. This expression is exactly equal to 1. So P of 1 is true. So we've proven the base case. All right. Step 2 is the inductive step. All right, we have to prove that P of n implies P of n plus 1. So prove P of n implies P of n plus 1. All right, how do we prove if P then Q? We start off by assuming P, we apply the rules of logic, algebra, and eventually we try to come up with something which is P of n plus 1. And as long as we're working logically through our proof, every proposition we write will be true, and so if we eventually can write P of n plus 1, we've proven that the conclusion follows from the hypothesis. And I'm not proving that P of n is true. That's a really hard thing to do. To prove P of n is true, I have to prove this. Well, I can't do that, right? That's too complex. All I'm proving is that if this is true, then P of n plus 1 is true. And that's not too hard. Okay, so step 1, P of n. Reason, that's the hypothesis. Step 2, just like even-odd proofs, I'm going to write out what this statement means. P of n is the statement that the sum from I equals 1 to n of I is equal to n times n plus 1 over 2. That's the definition of P of n. And now we're just going to do a bunch of algebra. All right. Well, so I'm going to make my ignore section over here, and these are going to be really important in these inductive proofs. So ignore this. what am I trying to do? I'm trying to prove P of n plus 1. Well, sometimes it's helpful to write out what it is we're trying to prove. So we want to prove P of n plus 1. Well, what is P of n plus 1? We want to prove that the sum from I equals 1 to n plus 1 of I is equal to n plus 1 times n plus 1 plus 1 over 2. If we can argue here and eventually state that this is true, we're done. We've proven P of n plus 1. We've got our inductive step. We put that together with our base case. We say mathematical induction, and we're done. So how can I show this given that? And this is where, there's usually one sort of spark of inspiration that comes in somewhere during these proofs, where we see some different way of looking at something or a way of rewriting something in a different form that suddenly makes everything else fall into place. Okay, it's a game. One thing that might occur to you is that here we have a sum of I from 1 to n. Here we have a sum of I from 1 to n plus 1. But that's really the sum from I equals 1 to n of I plus just one more term, which is n plus 1. This is this business of breaking up summations that we did back a few chapters ago, right? This is the same thing as this. This is the sum of the first n plus 1 integers. It's the sum of the first n integers plus integer n plus 1. And since we already have an interesting way of writing this sum like that, maybe we can plug this in for here and get something that'll turn into that. That's that sort of inspirational spark there. So you could work this out on scrap paper, right? But I'm just going to confidently write it on my main proof page here that I'm going to turn in. And I'm going to do the following. I'm going to write down the sum from I equals 1 to n plus 1 of I is equal to the sum from I equals 1 to n of I plus n plus 1. And that's, properties of summation. So we can pull a term out or a group of terms out. And I'm not using this. I'm not going to use this equality at all because I don't know that this is true. If I write this down in any way, shape, or form, my proof falls apart. But I'm not using this. Ignore. I'm just taking this and I'm saying it's the sum of the first n integers plus one more. Okay? But now I'm going to say that's equal to, and I'll be formal about this. I'll write down the left-hand side again. And that's equal to, but I'm going to replace this summation with n times n plus 1 over 2 plus n plus 1. And that's substituting 2 into 3. And now I'm not going to keep writing the left-hand side. I'm just going to keep modifying this right-hand side. I'm going to say this is n squared plus n over 2 plus n plus 1, which is equal to n squared plus n over 2 plus, and I'm going to rewrite n plus 1 as 2 times n plus 1 over 2. So I'm putting in a common denominator here. And that's n squared plus n over 2 plus, and I'm going to multiply out the 2n plus 2 over 2. And now I'm going to combine the numerators and say this is n squared plus n plus 2n plus 2, all divided by 2. And I'll continue combining. This is n squared plus 3n plus 2 divided by 2, which is equal to, and now I'm going to factor the top and say n squared plus 3n plus 2 divided by 2. That's n plus 2 times n plus 1 divided by 2. And the reason is lots of algebra. Let me rewrite this a little clearer. N plus 2. All right, I haven't used this equality at all. I simply started with the sum from 1 to n plus 1. I split it into two terms. Up here, I substituted this expression in for that summation, and then I did a lot of algebraic manipulations. But when I'm done with all of that, what have I got? I've proven that the sum from 1 to n plus 1 is equal to n plus 2 times n plus 1 over 2. So let me rewrite that. And let me swap my terms around. Let me might write it as n plus 1 times n plus 2 over 2. So we'll do a little more algebra here. And I'll rewrite n plus 2 as n plus 1 plus 1. All right, well now what have I done? P of n is the proposition. Oh, I'm on the wrong page. P of n is the proposition that the sum from 1 to n is n times n plus 1 over 2. P of n plus 1 would be the proposition that the sum from 1 to n plus 1 is n plus 1 times n plus 1 plus 1 over 2. So let me just make a little note here. Recall P of n is the proposition sum from I equals 1 to n of I equals n times n plus 1 over 2. P of k would be the proposition that the sum from I equals 1 to k of I is equal to k times k plus 1 over 2. Okay, let's just think of n as a variable. P of smiley face is the proposition that the sum from I equals 1 to smiley face of I is equal to smiley face times smiley face plus 1 divided by 2. Okay, this n is just a placeholder. So the statement of Pn plus 1 says the sum from I equals 1 to, instead of smiley face, n plus 1, of I is equal to, instead of smiley face, n plus 1, instead of smiley face plus 1, n plus 1 plus 1, divided by 2. That's what P of n plus 1 says. I'm not claiming this is true, I'm just stating the proposition. But guess what? From my previous work, I've proven this. This is P of n plus 1. That's exactly what I just proved. So from this, we can conclude P of n plus 1 is true, and the reason is that's the definition of P of n plus 1. All right, we've done the hardest part of the work. We just have to put the bow on it and tie it up nicely, right? So we've proven P of n plus 1, and we did that by assuming P of n. So what's this whole proof show? It shows that if P of n is true, P of n plus 1 is true. Therefore, P of n implies P of n plus 1. That's our inductive step. Taken together with our base case, we now apply mathematical induction and we conclude the following. P of n is true for all n bigger than or equal to 1, and the reason is mathematical induction. And that's what we were trying to show. And that's the end of our proof. Alright, so that's a number of pages and a lot of detail, and in practice, a lot of that detail will get done kind of in our heads, or with fewer lines, but I want to spell this out absolutely rigorously the first time through. Okay, because I want us to understand what's going on behind the scenes, even if we're kind of skipping some steps or doing things intuitively or something like that. All right, so questions about this? All right, let's do another mathematical example, and if we have time, let's do a non-mathematical one. So let's do a good computer science. Yeah, it definitely takes some practice, and it takes some sinking in. So we'll go through lots of examples. So let's talk about the sum of powers of 2. And we've seen this in computer science probably a number of times. If you do something like, 1 plus 2 plus 4 equals 7, well, that's the next power of 2 minus 1, right? If you do 1 plus 2 plus 4 plus 8, you get 15. That's the next power of 2 minus 1. And we bump into this all over the place. Computer Science, Engineering 250. What is this? This is the 4-bit number that looks like that. And we know that, if we add 1 to this, we get this, which is a power of 2. Right? So this is 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. This number is 2 to the 4. Well, this number is actually the sum of those powers of 2. And if we were to add 1 more to that, we would get 2 raised to the next power, 2 to the 4th. So consciously or subconsciously, we've probably brushed shoulders with this fact multiple times, that adding up consecutive powers of 2 gets us 1 less than the next power of 2. So let's prove that that's really a thing. So let P of n be the proposition sum from I equals 0 to n of 2 to the I equals 2 to the n plus 1 minus 1. So what does P of 1 say? P of 1 says sum from I equals 0 to 1 of 2 to the I should be equal to 2 to the n is 1, so 2 to the 2 minus 1, which is 3. What do we get if we add to the I from I goes from 0 to 1? Well, this expression is 2 to the 0 plus 2 to the 1. 2 to the 0 is 1, 2 to the 1 is 2. This expression is equal to 3. That's what the right-hand side is equal to. So P of 1 is true. All right, so let's prove that P of n implies P of n plus 1 for all n bigger than or equal to 1. Again, we're not proving P of n. We're not proving P of n plus 1. We're proving if this, then that. Simpler statement. All right, step 1, P of n, that's the hypothesis. Step 2, I'm going to replace P of n with what it says, which is the sum from I equals 0 to n of 2 to the I equals 2 to the n plus 1 minus 1. That's the definition of P of n. All right, let's think out loud. In our ignore section, what does P of n plus 1 say? Sum from I equals 0 to n plus 1 of 2 to the I should be 2 to the, it'll turn out to be n plus 2 minus 1. All right, n plus 1 plus 1. And again, the same kind of inspiration that we had in adding consecutive integers. This is really just this with one more term added. So let's write an equality for our third proposition. Let's write an equality that we know is true without doing any assumptions. Let's state that the sum from I equals 0 to n plus 1 of 2 to the I is the sum from 0 to n plus, let's be formal, sum from I equals n plus 1 to n plus 1 of 2 to the I. That's the way we formally break up a sum, right? Go from 0 to n, and then from n plus 1 to whatever that top range was. And let me just string out all the algebra over here, because we're running a little short on time. I know the sum from n plus 1 to n plus 1 of 2 to the I, it's just 2 to the n plus 1, right? Because this only has a single term in it. And then I'm going to go ahead and substitute in place of the sum from I equals 0 to n, I'm going to substitute this. So this is going to, and don't do this on your homework, because this is no longer a formal proof when you start drawing arrows and leading the person on a treasure hunt, but I'm just doing this for time convenience. Let's see, wait, why wouldn't it be I equals n? I don't know where you mean. But here's the sum from 0 to n, here's the sum from n plus 1 to n plus 1. So 0 to n, 2 to the I, and then n plus 1 will be 2 to the n plus 1. No, if I'm going to n here, then I have to start from the next term here, n plus 1. Right, so the sum from a to b can be the sum from a to n, and then the sum from n plus 1 to b. Otherwise, you'd be counting n twice. Alright, so let's just substitute 2 to the n plus 1 minus 1 in place of this term. This sum will be equal to 2 to the n plus 1 minus 1 plus, and then this term 2 to the n plus 1. And now if we just do some rearrangement, this will be 2 to the n plus 1 plus 2 to the n plus 1 minus 1. And this term is written twice, so that's 2 times 2 to the n plus 1 minus 1. And powers of 2, 2 to the n plus 1 times 2, this will be 2 to the n plus 2 minus 1, which is 2 to the n plus 1 minus 1. And bingo, we're done. We have shown that the sum of the first from 0 to n plus 1 of 2 to the I is 2 to the n plus 1 minus 1, right? That's what we were working towards. That's the statement of p of n plus 1. So now we can say, therefore, p of n plus 1. And you're not done yet. You've done the clever, intuitive part, but you still need to bundle it up. So we know p of n plus 1 is true. And we got that by starting with p of n. Therefore, p of n implies p of n plus 1. And we did a base case. We showed that p of 1 is true. And so therefore, p of n is true for all n bigger than or equal to 1. And the reason is mathematical induction, and that's what we were asked to show. Alright, so this is what all of our inductive proofs will most of our inductive proofs will feel like. Okay? It's stating what you're told, and then finding a way to turn it into, part of what you're trying to show, which is p of n plus 1, and then using logic, algebra, things like that, to somehow turn that into a formal statement of p of n plus 1, so that we can show this implication. And that's the whole goal in a proof by induction, is proving this, if this, then that. Right? And you put that together with a base case, which is usually just something that you demonstrate because it's a particular value of n, it's a particular proposition. And then you say, therefore by mathematical induction, p of n for all n in whatever range we're looking at. And that's what we're trying to show. All right, so we will absolutely spend a lot of time Monday and Wednesday going through lots of examples of mathematical induction. We'll do some examples that are not mathematical in nature. We'll look at covering floors with tiles. We'll look at throwing pies at people in a room. And we'll look at a collection of horses in a field and ask whether or not they're all the same color. And we'll go from there. All right. So have a great weekend, or good luck on your exam if you have an exam right after this, and then have a good weekend, and I will see you next time. And I've got office hours at 3 if people need to pop in there. All right, thanks. Bye.